Hi, this video is intended to be embedded into a longer video on completing the square. So if you were watching that video on completing the square, hopefully you clicked over here from that video. If you just kind of clicked on this video randomly, go ahead and check out the lesson on completing the square so you can get the lead up to what we're about to do, and then go back to it and get the algebraic summary, and we're going to tie it all together with the algebra tiles. But what I'm going to do here is work through two examples from that lesson. So we're going to start with the example x squared plus 4x. So I'm going to drag over. We have 1x squared plus 4x minus 1. And right now, if you're familiar with algebra tiles, and if you're not familiar with algebra tiles, please go check out some of the videos on the algebra tiles list playlist so that you can get an idea of how these work. But we've got x squared plus 4x minus 1, and this would be in what we call standard form. And what we're going to do is this process called completing a square. Now, there's an algebraic way of thinking of completing the square, but what I love about algebra tiles is it's going to be very geometric. We are literally going to take these tiles and make the biggest square we can make with them. And so I'm going to start with the blue square here, and I'm going to start adding on to the width and the height. Okay, so I know if I add something onto the width and I make the width a little bit longer, I'm going to have to add the same amount onto the height, okay, in order to keep it a square. So adding a little bit onto the width, now I'm going to add a little bit more onto the width. But again, if my goal here is to make a square, I am going to have to add the same amount onto the height. And so what we have here is we have the width of the square and the height of the square. They have to be the same. Okay, so we're keeping those two dimensions the same. Now we kind of run into a problem, all right? Because this cannot fit in there for two reasons. One, it does not complete the square. Okay, this is an incomplete square if you ever saw one. The other reason we can't put that there is these x's are positive. And remember, this dimension here is a positive 1, and this is positive 1. And positive 1 times positive 1 cannot give me a negative 1. The algebra tiles feed into what's called the area model, where we're actually modeling all of this with area. So 1 times 1 can't give me negative 1. So we have that dual problem there. So here's our solution. If I have like 1 and 1, 1 times 1 is 1, or you could think of it as we have a dimension of 2 times the dimension of 2. So we need 2 by 2 or 4. In order to complete that square, I need 4 ones. But as soon as I import those ones, I have changed the value of the polynomial. When I import them, I have to import them as what's called a zero pair. And so when we bring in those 4 ones, we got to bring in these negative ones to balance them out so that we're not changing the value of the polynomial. And now I've got the correct tiles here to literally complete the square. And these negative ones over here come and join my extras. And so what I've done is I have rewritten this polynomial as a completed square. The width and height of the square here are x plus 2. So it would be x plus 2 times x plus 2, or x plus 2 all squared, okay, minus 5. I'm going to have a minus 5 on the outside. So that's what the process of completing the square looks like with algebra tiles. That's your reasoning through it. Now, the second example is x squared minus 2x. So this time we'll bring over the minus 2x plus 3. And this one's going to have a little bit of a different feel to it. Now, same deal. We're going to take this polynomial and we are literally going to make a square. Okay, and to make a square, I'm going to have to add the same amount to my height and width in order to keep those dimensions the same. And what I want you to notice there is that the only way to do this is to take your x's and split them in half. And then you add some of them to the width and some of them to the height. That's the only way that's going to work. You could try to juggle this around and say, well, I'd like to put it down here, but that will never ever get you a square. So the only way to do that is to take your x's and divide by 2. Now, we've got -1 times -1, which is a positive one. So you might be tempted to say, let's just put that in there. That will complete our square. And then I'll have 2 left over. And so it would be x minus 1 all squared, x minus 1 times x minus 1 plus 2. However, and yes, you can do that. That works in theory. But in order to hold the procedure consistent, I'm going to do the procedure the same way I did it in the previous one. So instead of just grabbing a 1 from here, we're going to import what we need. We're just going to need to import it along with its 0 pair twin there. And I'm going to put this 1 in the corner to complete the square, and then add the -1 to my collection. And then you'll notice we have a 0 pair. And so I can take it out. And I am 100% aware that you're probably looking at that and saying, but that would have been just easier if you had just taken the 1. Yes, but remember that the last problem didn't work that way and we had to import the 0 pairs. So this one, it turns out we didn't, but what we want to aim for is a process that is going to work all the time. And so we don't want to take a little shortcut with this one because it only works for this one. All right, so my final completing of the square, I get x minus 1 all squared plus 2. So now that we've finished these 2 examples, go ahead, click back over to the lesson video, and we'll try to summarize and turn this into an algebraic process we can continue with.